These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. Well, let's start by trying this problem.
Okay. X equals 1, so I'm not sure where to go right now.
Okay, so you might have forgotten how to use the point slope formula for a line. So let's review that. Let's back
Okay.
up for a second. So let's see, you have your curve. Now, we need to improve our notation for some of the previous lines. So the third line you have written down is y prime equals 4x cubed minus 8x plus 3. Then in the next line, you're doing something different, but it's still labeled as y prime. So we need to improve that label a little bit to show how the third line and the fourth line are different from each other.
Okay. So no. Okay.
Okay, why did you write down the letter y?
Because we're plugging x in onto this side, and that's going to give us what y is.
Why do you say that? What are we plugging x into?
We're plugging x into... Okay, this would be for the slope.
Okay, well, let's talk about that notation a little bit. So what I was going for here is, so yeah, what did you, tell me, what did you plug the x equals 1 into? Point to where you pointed it, where you plugged it in.
Right here.
So notice you didn't plug it in for y.
Okay.
You plugged it into the formula for y prime.
For derivative.
That's right. So notice what you have now is you have two different functions written down. Well, what's a function? A function is a rule that takes an input and changes it into an output. You now have two different functions written down. The first function is called y. And the input there, if you put in x, you'll get out a y. And then your second function is called y prime, where if you put in an x, you get out the y prime. So which one of those did you plug the x into?
We plugged the x into y prime.
That's right. In the next line. So the notation I was going for is that we should be writing y prime parenthesis 1. You were close, but you didn't quite get that. Okay. What was the name of the original function here?
The name of that function is...
What was the name of the original function we started with?
That's... I guess it's...
Maybe that question didn't make sense. The name of the original function is y.
Oh. Okay.
Right? The first function we dealt with here was the y function. Y equals x to the fourth minus 4x squared. Okay, so this is something that we've been doing in the past and not having much trouble with it. So why did it give us trouble here? It's just because we changed the names around. What are you used to us calling the functions? You're used to us calling the functions f. I'll bet if this function was called f, you wouldn't have had much trouble writing down the labels. We've done that many times. But in this case, we changed the name of the function from f to y, and it looks like that threw off our intuition. But if you look at it now, we're using similar notation to what we've used before. The first line you wrote as y equals x to the fourth minus 4x squared plus 3x, and that's perfectly fine. But another way you could have written that is as y of x, y parenthesis x equals x to the fourth minus 4x squared plus 3x. That way it would be more consistent with our previous notation. And how about your second line? Your third line you wrote as y prime equals 4x cubed minus 8x plus 3. That's fine. That's a perfectly good way to write it. But it would have been more consistent with our earlier notation to say that that was y prime of x. So like I'm saying, the way you wrote it was acceptable. But to show how it was similar to what we did before, we could have called those lines y of x and y prime of x. And then it would be clearer to you that what you're doing in the fourth line is you're doing y prime of 1. Now that you have written it like we've written it like that, we can see that this is very similar to what we've done in all the previous problems. The only reason that we lost our intuition is because we changed the name of the function from f to y. Why did we do that? Why did we change the name of the function from f to y? Well, it's just because when we graph functions, we tend to call them y. So since we're looking at this graphically, they changed it from f to y in this case. The name of the function is completely irrelevant. We can call the function whatever we want. If we want to, we can call it ln. We could start with ln of x, and then we can figure out ln prime of x. So the name of the function is just it is arbitrary. We're still going through the same pattern as we did before. Okay. So it's always good to try to make sure that we're coming up with good labels for each line so we know what they represent. All right, so let's see. So you got y prime of 1 was negative 1, right? Mm-hmm. Good. Now we've worked on interpreting derivatives. Let's put the problem aside for a second and just interpret that answer. How have we learned to interpret that negative 1 answer?
Okay, so as x moves from 1 to 2, the value of the function, well, the function decreases by 1.
That's right. What's the name of the function?
The name of the function is y.
So you could also say that as x increases from 1 to 2, the function y decreases by 1. Although we have to be more careful, we should have said y decreases by approximately 1. The derivative only tells us the approximate change. So here we're saying as x increases by 1, y decreases by approximately 1. Yeah, as x goes up from 1 to 2, y is decreasing by approximately 1. Okay. Well, that's one of the interpretations we've worked on. We've also worked on the graphical interpretation. What's the graphical interpretation of that -1 number?
Okay. When x is 1, the slope of the tangent line to the function is -1.
Good. Excellent. That's exactly right. Good. Okay. And now we're trying to actually write down the equation for that tangent line. So you're using the point slope form. Now, the way you wrote that isn't quite the most useful way. So we're trying to get the equation of a line, right? Now, the equation of a line has variables in it. What are going to be the variables in our equation?
We're going to have y, x, and m.
Okay, now that wasn't quite right because m is not going to be a variable in our final equation.
Okay.
M is going to be a constant. What are going to be the variables in our final equation, y and x? So yeah, what you had before was pretty good. We didn't have to erase everything. I was just going to say that you needed a y and an x in there rather than a y2 and an x2 so that it looks like the way we normally write those. So the best way to write this is y minus y1 equals m times x minus x1. So that's an equation we should memorize. So which of those symbols stand for variables in this problem?
Y and y1 and x and x1.
Turns out that only y and x are variables. We'll see in a moment that y1, x1, and m are going to stand for constants.
Okay.
All right, so let's go about plugging stuff in. So since y is a variable, we're not going to plug anything in for that. So we'll just write down y again. Minus y1. Maybe we're not quite ready to plug in for that yet. What can we plug in for m?
-1.
Okay. And then x is still a variable. What can we plug in for x1?
For x1, we can plug in 1.
Okay. Then what can we plug? How can we figure out what to plug in for y1?
For y1, we can plug x into the function.
So let's work that out.
Okay. Okay, so
Okay, good. Now that's a good use of labels. Notice how on your left here now you have two different things, y of 1 and y prime of 1. It's very important not to confuse those two things. They tell us completely different information. Okay. All right, well, we could stop right here. Now we have an equation of a line. I think on the test your instructor might want you to solve for y. So you can solve that equation for y.
okay, solve for y. Okay.
Okay, and that would be another equation for the line. Okay, so, so what does that y equals negative x minus x1 represent?
Y equals negative x plus 1 is the equation of the function.
Of which function? We already know the equation of the original function was x to the fourth minus 4x squared plus 3x.
So this represents
Why did we even bother figuring out that equation? Y equals negative x plus 1.
Oh, because we're trying to find the tangent line.
So what does the equation represent?
The tangent line to the curve y of x
Yes, it's the equation of the tangent line to the original curve. At the point x equals 1. Okay. All right. Well, that gave us some trouble, but there's a good chance you'll see that on the test. So let's see. What do we need to work on here? So what's the point slope formula for a line? Good. Which of those letters stands for variables?
y1 and x1.
Which of those letters stand for variables?
X and y.
Yeah. And which of those letters stand for constants?
M, y1, and x1.
That's right. Now, when I said that before, you might not have quite understood what I meant, but now it should be more apparent because we did plug in constants for y1, x1, and m, right? Notice that eventually the y1, the x1, and the m disappeared and were replaced by numbers, whereas we didn't plug in anything for the x and the y. We left those as variables in that equation.
Okay.
So that's what I meant by distinguishing between which of those are standing for variables and which are standing for constants. This slightly contradicts what we said previously, because previously I told you that usually letters from the end of the alphabet stand for variables. But in this case, x1 and y1 are standing for a constant. So that somewhat contradicts one of the ideas that we said before, as an exception to that. Okay, so that's the equation we use to find the equation of a line. And then how do you use that? Well, remember, why is that called the point slope equation of a line? Why is that called the point slope equation of a line?
Because it's giving us the slope from one point to the other.
Not really. The reason it's called the point slope equation is because it's an equation that is convenient to use if you know one of the points on the line and the slope of the line. This is an equation that's convenient for us to use when we know one of the points on the line and we know the slope of the line. Do you see how it was convenient for us to use when we know one of the points and the slope? Because it gives us places to plug in the point and the slope. So the point is, if you know one of the points on the line and the slope of the line, then you can plug them into that equation. Where do we plug in the slope?
To m.
And where do we plug in the point that we know?
It depends on what they give you. So in this case, they give us x, so we plug it into x1.
Well, that's true, but we're still going to have to plug in y1 as well. So my point is, where do we plug in the point? We plug in the point as x1 and y1. X1 and y1 represent the point that one of the points that we know on the tangent line, and m represents the slope. Remember, when you first wrote down the equation, you were writing also y2 and x2. But we can see how that wouldn't help so much, because then we wouldn't get an equation that's about y and x, which is the way equations usually look. Okay, well, we'll do a little more practice with that to get the hang of it. But let's try drawing a graph of what was going on here to try to build our intuition. Maybe we should scroll down and give us some space. So try to draw a graph that represents what we've just been seeing here. I've actually done that for you a couple times in the past. So let's try drawing a graph. Let's make it a pretty big graph so we have lots of space to show stuff here. And you can use your calculator as needed to draw that graph.
Okay. So at when y is 0 and x is 1.
So the first thing you should do is draw the curve.
Okay. Well, I'm trying to zoom out so I can see the curve, but it's not wanting to go. Okay, there we go. Something like that.
Okay.
All right. So this is so x is 1, y is 0. So slope would be going downwards. I don't see how you can draw a
So
tangent line.
next, let's put a dot at the point that we're focusing on. So which point on the curve are we focusing on?
X is 1, x 1, 0, I guess.
Good. Now you can see then that your graph has to be erased and redrawn a little bit because so that the curve actually goes through that point.
That's, I guess my calculator is, I don't know.
Sorry, what are you trying to do?
I was trying to graph it on my calculator, and it seems like it's past the first tick mark, so I assume that was, it wasn't going through 1, but I guess you have to use some, I guess you just have to assume it goes through the point you're looking for. I don't.
Well, we already know that it goes through 1, 0 from the work that we did previously. Remember that maybe you should scroll back up. We tried to figure out what was the y coordinate when x was 1, right?
Mm-hmm.
Do you see up above where you saw that y of 1 is 0?
Mm-hmm.
So our work already tells us that the curve goes through 1, 0. That's what that equation means. So maybe after we're done with this, I'll go back to my calculator and maybe we'll see how to see that more clearly. But we know from our previous work already that it goes through 1, 0. This is where it helps to draw a bigger graph. Notice how you've, or you can zoom in. Notice how you drew the tick marks out to 5, but since all we cared about was 1, 0, there was really no reason to draw those tick marks all the way out to 5.
Okay. I see.
And I think if you look at your calculator, you can see it dips below the x-axis slightly.
I'm not sure how to zoom, so
Okay, well, we'll stick with that for the time being. So let's put in a dot at the point we're focusing on. Good. All right, now draw the, so let's label the curve that you have written down so far. What's the equation of that curve? Okay, excellent. Now let's draw the tangent line. Now, draw the, what's the point that the tangent line is going through?
1, 0.
Right. So put your cursor there. Is the graph upward or downward sloping at that point?
It's downward sloping.
So that means the tangent line must be downward sloping too.
Mm-hmm. I just thought the tangent line wasn't supposed to touch the graph. So
Well, the tangent line will just skim the graph at 1, 0. It can cross the graph at other places.
okay.
Okay?
Okay.
And let's write down the equation of that line. Okay, good. What's the slope of that line?
The slope of this line is -1.
Does that mean it should be upward or downward sloping?
Downward sloping.
So that's the other way to see that our earlier tangent line couldn't have been correct. An upward sloping line can't have a slope of -1. All right, let's label the axes. Okay, very good. All right, so so this is what all of our work that we did previously represents. All the work that we did previously was to work this out. How did we? Let's see. So the point we're focusing on. What's the point we're focusing on?
We're trying to find this equation, which is the equation.
I'm sorry. What's the particular point on the
Okay.
graph that we're focusing on? What are the
One's-
coordinates of the point?
1, 0.
Good. How did we get that number 0?
We got this by plugging 1 into 1 into this function right here, which is
Yes, that's right. We plugged 1 into that function because we wanted to know what the y-coordinate would be when the x-coordinate was 0. Good. And now, what's the slope of the tangent line?
the slope of the tangent line is -1.
How did we figure out that -1 number?
We plugged in 1 into the derivative. Yeah, derivative.
Which we haven't graphed, right?
Right.
Notice that we haven't drawn the derivative on this graph. So notice, you can see how confusing this is. We got 3 different functions running around now. We have the original y of x equals x to the 4th minus 4x squared plus 3x, the equation of the curve. And we have the tangent line to the curve, y equals -x plus 1. That's another function. And we have another function we haven't even graphed, which is the derivative function, y prime. We haven't actually drawn that on the graph, but we used it to find the slope. So we've got lots of different functions running around. It's certainly easy to get confused between all of them. Okay. So let's see. Let me. I think I'm going to go back to my screen for a moment now, so I can. So we can go through how to do this on the calculator. Maybe you might want to follow along with this. So let's see. I'm going to go to y equals, and then we've got x to the 4th minus 4x squared plus 3x. By the way, notice it's too late now, but it looks like we miscopied the problem, because the original problem I wrote down was +3.
Yep.
But it looks like we miscopied it. But all right, so it doesn't matter. So we ended up doing this function instead. This is the function we ended up actually doing. Okay, so let's see. All right, so you type this function in, then you hit graph.
Yep. And I see it normally now, but before it was really zoomed in, so I was going to zoom and then zoom out, but it wasn't really working.
So one thing you can do is, first of all, one thing you might always do at the start of a new problem is go to zoom and go to standard. That kind of puts you back to your defaults.
Okay.
So if your zoom doesn't seem good, you can always go to zoom standard, and that'll get you back to your defaults.
Cool.
Now, these tick marks here, I guess, stand for like 1, 2, 3, 4, 5, 6. So what would be the next thing we should do? Well, this is where it might help to follow along. Now let's hit trace. And we want to go to where x equals 1. So I've hit trace, and I think I can just now hit 1. And notice it knows that I want that to be the x. Now we hit enter, and it's put us where x is 1. Did that work on your calculator?
Yep.
Okay, and notice it even told us that when x is 1, what's the y-coordinate?
0.
In fact, that's something we had to figure out ourselves laboriously, but the calculators told us that for us. how did the calculator get this number 0?
It got 0 by plugging in 1 into the function.
Which function?
Well, it's just y of x.
X to the 4th minus 4x squared
Oh,
plus
okay.
3x. Yeah.
Right.
As you can see, it has it up here, which is the function it's dealing with. Now, it's kind of hard to see what the graph is doing right here, right? It's hard to see if it's above the axis or whatnot. So let's continue on together. We can go to zoom, and we want to zoom in. And we want to zoom in around where x is 1. Okay. Well, it looks like we're already there because of our tracing, right? So we've already around where x equals 1. So now we just hit enter.
Okay. That's what I wasn't doing.
All right. And now we can see where we are now, and we can see what the graph looks like more. But even now, I don't like this still because it's hard to see what the graph is doing exactly. So what happens if I enter again? I lost my axes, but it zoomed in even a little bit more. Mm-hmm. And now we can see that it does dip below the axis. And now I can hit trace again and go to exactly where x is 1. And I can see that's this point here. And now we can see clearly that the graph really is downward sloping. The tangent really is downward sloping at this point. What can I do to zoom out here to get back to the normal zoom?
The down arrow key? Or?
Well, we could. The easiest thing is, remember, we can always go back to zoom standard.
Okay.
There's a couple different things you could do, but you could always just go back to zoom standard. Did that work on your calculator?
Yep.
Okay, so those are some zoom techniques. So what we were going over is how to zoom and also how to go to a particular point on the graph. You can hit trace and then tell it what the x-coordinate is so you can go to that particular point. And then you can go to zoom in and then hit enter to zoom in on that point. Okay, so we have that graph. Maybe I'll go back to standard now. So this is part B for the same curve. So the curve is the same as before. Now let's try this.
Okay. I'm just going to go with 3x.
Sure.
Okay, so
Can you, let's see. It's hard for me to read writing there. You have y prime of x equals, and then what's the next thing you wrote?
that's minus 16. Wait, sorry. Yeah.
All right. How did you get that minus 16?
I plugged 2 into 4.
Okay.
Sorry.
So what did you plug in as your input?
-2.
Okay. And what function did you plug it into?
I plugged it into, okay, this is bad. I plugged it into the original
What's the name
function.
of the original function?
X to the fourth minus 4x
Right,
squared
or
plus
y of x.
5x.
But you labeled it as y prime of x. So
Mm-hmm.
we need to do something that's consistent with our label. Notice that that's the same exact derivative we got before because we haven't changed the curve.
Right. -16 plus 3, -13. Okay, so slope equals -13.
Okay. And what's the label for that last line that you just worked out? The -32 plus 16 plus 3. What label did you write down for that line?
Slope.
On the left.
Okay.
Each of those equations is written. First, you had y of x equals x to the fourth minus 4x
Right.
squared plus 3x. So what's the label for the line we just did?
This is y prime of -2.
Right. Not y prime of x. That was the previous line, right? The previous line tells you what y prime is for any x, but then we figured it out for -2.
So y of -2 would be 16 plus 16 minus 6. So y equals, well,
How did you get that -34 number?
-34 I got by oh, that's incorrect.
Okay, good. So let's see. What's the slope of the tangent line?
The slope of the tangent line is, it's -13.
Okay, good. Now let's draw a graph of that, but let's put that on our previous graph so we can compare our two answers. Hopefully our previous graph is big enough to fit that in.
-2, 1, 2, 3, 4. Well, this comes down farther. I didn't draw it. So let me go back to this. Trace assume that was the tangent line. I'm just really bad at drawing or
It's a
writing.
little tricky on the tablet as well. But the key thing is just to get close enough so that we're building our understanding of what we're doing.
Okay, so I need to draw the tangent line to this point. The slope is negative, so it's downward. But
And it's just skim along the curve. It's hard to draw, but that looks good.
something like that, I think.
Okay. Now, what's the equation of that line you just drew? Okay, good.
Okay.
So it's useful, I think, here to see that you can find. In the past, we've been talking about finding the tangent line at a point, but you might not have quite understood what we meant by at a point. But now you can see every single point has its own tangent line, right? Theoretically, we could draw an infinite number of tangent lines here. We've drawn two now on the same graph. Where was the graph steeper? X equals 1 or negative 2, x equals negative 2?
X equals negative 2.
Because what's the slope of this line?
It's negative 13.
That's right. And you can see from your graph that you did draw a steeper line there, whereas the line up above is much shallower. So, the slope that we're getting is matching up with what came from the graph there. Okay. Let's see. So we still had trouble with that step. So let's try one more point on this graph. Let's find the slope of the tangent line at x equals 4.
Okay.
So for the same curve, let's find the slope of the tangent line at x equals 4.
Four times 4. What? Okay.
Notice that you didn't actually have to figure out the derivative function, and because you could just, the derivative function is the same as before. You just had to evaluate it at a new point. Good.
So this is going to give us y when x equals 4. So I'm going to use the original function x. 56 minus 64. Two oh four, and x equals 4, y equals 204, and slope equals 227. So
Good.
plus 204. Okay, here's the slope. What? Sorry, not the slope. Here's the equation of the tangent line to the function when x equals -2.
Great. Let's try to put that on the graph. It'll be a little tough because it's kind of off the graph. We'll just have to fudge it a little bit. But as best we can, let's try to graph our results here on the same
Okay.
graph that we did before.
Okay, when x is -2, y is 204. And the slope was something.
What value of x did you just use?
4.
Good.
And
Good.
the slope was 227x minus 704. Okay.
Okay. That y equals 227x minus 704. What's that the equation of?
The tangent line to the function at x equals x equals 4.
Okay, good. What's the slope of that line you just drew?
227.
What does that mean that the slope is 227? What does it mean that it's such a big number?
That the slope is going upwards, almost completely vertical.
Yeah, so is it steep or shallow?
It's very steep.
Yeah, upwards or downwards.
Upwards.
Does that match what you have on your graph, what you have on the calculator?
Yep.
Yeah, you can see, actually, if you look at your calculator, the calculator never even made it out to the 4th hash mark. The calculator it goes off the screen before the 4th hash mark because you can see it's so steep that it can't fit that on the screen, right? Because it's going all the way up to, what, 227 or something? All right, so obviously we can't really draw this accurately with this. We can't really draw all these points on the same graph here, but we know that this point is very high up on the graph because it's extremely steep at that point. Okay, well, hopefully this little exercise gave us a better intuition for what they mean when they say draw the tangent line to the graph at a certain point and what the method is for that and how to use the calculator to help us with that. I'll go back to my screen now.
Okay.
Let's try this problem.
Okay.
It's not going to work out very well. Let me try something else.
Okay.
Let's just do this.
Y equals square root of x.
Yeah.
Okay. So y of x is square root of x. Which equals x times that one half. And find the slope, plug in one magnitude to the derivative, and divide this one, and 0.5. Okay, so that's our slope equals 0.5, x equals 1, now y1 is going to equal 1. So y minus 1 equals Alright, let's mix up this one. Okay, there's the answer, and then I get word practice after graph, right?
Good.
Okay, so this one, calculator. X equals 1. slope was positive.
Good.
Okay.
Okay, good. So those are some good labels. Let's label the axes. Okay, good. All right, good. So that's good practice with the tangent line. Now, so why do we care about the tangent line? How is it useful? Well, one way it's useful is, do you see that the tangent line is close to the function? It's a good approximation to the function, as long as you don't get too far away from x equals 1. When x is close to 1, the tangent line is very close to the function, so we can use the tangent line to approximate the function. If we want to know how much the function is going to change, we can just see how much the tangent line is changing. That'll give us the approximate change in the function as well. On the other hand, you can see that if x was a long way from 1, then the tangent line would not be a very good approximation anymore. Okay, so that's one. So why do we care about derivatives? Well, one reason is because they tell us the slope of the tangent line. And why do we care about the tangent line? Because it gives us a way to approximate the function. Why do we need to approximate the function? Why not just use the actual function? Well, the reason is because the actual function is complicated. It's got a square root in it. But the tangent line is much simpler. It's just a line. So it's oftentimes useful to use an approximation when it's simpler than to get an exact answer that's more complicated.
Okay.
All right, good. All right, I'll go back to, and as you go through the course, you'll see more examples. Go back to my screen now. Let's try this problem.
Version of the tangent line. Okay. E to x is 1 plus. x equals 1. So we'll find our slope. Oh. E to the 1 is 2 points. Okay. So E times 2 minus E times 2. So 0 over 4. E times 2 minus E times 2. 0. Okay. So the slope is 0. And now we're going to find its original function. So 1 over 2. So x1 equals 1. And oh, well, we were already given that, so I guess this point was pointless. Unless I'm misunderstanding. Okay, so anyways, we have that again. Although there's an E there, so. Okay.
So how did you get that y of 1 equals 1/2? Where did that come from?
I got this by plugging 1 back into this function.
Show me how that works out.
So E to the 1. Yeah, that's not correct. So E over 2.
So let's stop and talk about that for a moment. How could you have seen, you actually were pretty close to seeing that your first answer was incorrect. What was the thing that told us that our first answer for y1 was incorrect?
It didn't match this value.
Yeah. Does what we have match the value now?
Mm-hmm.
Yeah. One thing that might have thrown you off, do you see how this problem is a little bit nicer than the problems I was giving you before? Because before I was only giving you x1 and you had to figure out y1. But in this problem, you don't have to figure out y1 because it's given. It's still good practice to figure out y1. But if you go ahead and figure out y1, it should only confirm what you were already told in the problem. Okay.
But we still have to figure out the slope, right?
That's true. The problem
Okay.
didn't tell you the slope. It only told you both x1 and y1.
Okay. Okay, so now we have that, and we've figured out the slope was the net when of this step. Okay. So 0, well, y equals e over 2. It's the equation.
You just you miswrote that last coordinate.
Okay, so this would be the answer, I believe. Yep.
Good. Okay.
Wait.
Good. That's a good process. So that was a good use of labels. Let's scroll up so I can see it again. All right. So that was good practice with our derivatives. That looks like a good use of labels. This is the first time we've had a slope of 0, but you adapted to that and worked out what the equation was nevertheless. The one thing that was giving us trouble was finding y1. But in this problem, they actually told us what y1 was, so we could check our work on that. And let's go ahead and graph our results here again to build our understanding.
Okay.
I guess after this, we'll need a new canvas.
Okay, so the function was e of x one plus cool. And we're interested in x. Okay, so and then our slope was actually 0, so we're gonna get um, okay.
Okay, good. So what does it mean if the slope of the tangent line is positive? If the slope of the tangent line is positive, is the tangent line upward or downward sloping?
It's upward sloping.
And what does it mean if the slope of the tangent line is negative?
It's downwards
Now, what was
sloping.
the slope of this tangent line?
It was 0.
Maybe we should add that to our graph, because that was one of the main things we worked out, right? That
Mhm.
line has a slope of 0. What does it mean when the tangent line has a slope of 0?
It means it's horizontal.
Exactly. Is that what, is the tangent line really horizontal on the calculator graph?
Yep.
Now, they didn't draw the tangent line, but the point is the graph horizontal? I mean, is the curve horizontal at that point?
Yeah.
Yeah, it really is. The curve really is horizontal at that point. So you can see that the calculator is confirming that our calculus came out correctly. I noticed that when you first got that slope of 0, you were a little worried that you might have made an arithmetic mistake. But if you then graphed the function, you could confirm that the function function really is 0. It really is horizontal at that point. I'll go
Okay.
back to my screen.
So maybe I should graph the function as step 1, perhaps. Just
If that works for you,
okay.
that might be a good idea. Sure, whichever order works for you, but that might be a good idea. Yeah. Okay. So the only problem is if you make a calculator mistake, then you might think that your paperwork is wrong when it was really the calculator. But as long as you're doing it correctly on the calculator, yeah. Going back to my calculator here, so you had the function that you were graphing was e to the x divided by, so I guess you remembered to put in this set of parentheses?
Mm-hmm.
Good. Otherwise, it's not going to come out right. That's the kind of calculator mistake you could make. Now, what I would do next here now is I would trace to go to x1. Then I would zoom in. I hit enter because I'm where I want to zoom in. And now you can see more clearly that the graph really is horizontal at this
Mm-hmm.
point. That just confirms what we saw before. Also, you can see you didn't quite draw accurately what was happening on this part of the graph. I think you drew this part of the graph as also horizontal, where it crosses the y-axis, whereas it's actually upward sloping. That's really no big deal because this was the part of the graph that we cared about the most. Let's start by doing this problem.
Okay. Okay.
Okay, that's a good process. Let's also draw a graph of what that represents.
Okay, so what was y was 1. Okay. So should have drawn the graph bigger, I guess.
Well, I think that's a good job. That's a good job drawing the graph, and our interpretation, you labeled which is the tangent line and which is the original function. One more thing we can put in there, what is the slope of that tangent line?
Slope is -1, so
Why don't we write down slope equals -1 and then an arrow pointing to the tangent line.
okay.
What does it mean graphically when the slope is negative?
And it means that it's going downwards.
It means,
downward sloping.
yeah, who's it?
The slope of the tangent line. Well,
It means the tangent line is downward sloping, which also means that the function is downward sloping at that point, right?
Mm-hmm.
Now, is that how it turned out? Was the function really downward sloping at that point?
Yep.
Yeah. So I suppose what you did here is first you graphed the function on your calculator. And you can see on your calculator that the function really is downward sloping at that point. So that's a way to check that our derivative came out correctly. Okay, good. What's the point of this? What's the point of working out the tangent line? Well, remember, one point is the tangent line is a good approximation to the function when we're close to pi over 2. Notice that your tangent, it was hard to draw the tangent line because it's pretty much right on top of the function when you're close to pi over 2. Of course, if you were a long way away from pi over 2, it wouldn't be a good approximation anymore. Why should we use an approximation when we know the original function? Well, just because the equation for the tangent line is so much simpler. notice, compare the equation for your tangent line with the equation for the function. The equation for the tangent line is just y equals negative x plus a constant. It's a very simple equation to work with. But notice what a complicated equation the function has. Y equals e to the cosine x. Pretty complicated. So it's best, so the tangent line is only an approximation, but the advantage is it gives us a simpler function. One more thing we could do is this, since this is a trig problem, try going to your zoom menu.
Okay.
Or actually, maybe I'll do this on my screen. So I'll go back to my screen. So we've got e, was the function? Yeah, e to the cosine x. And then we can graph that. So is this what your graph looked like?
Yep, and then I zoomed in at x equals pi over 2.
Excellent. Good. What do all these little hash marks mean? I think these all stand for 1 unit. However, since we're doing trig, it might be more useful to go follow along on your calculator to this zoom that's specially designed for trig. Do you have that on your calculator?
Mm-hmm.
So let's hit equals. And you get something like this.
Yep.
Now, again, I'm going to trace pi over 2. That puts me here. So notice now, what do the hash marks stand for?
The hash mark stands for 1 still.
Well, notice I just put myself at pi over 2, right?
Right.
And that's exactly what the hash mark is.
Okay.
So what does this hash mark stand for on the x-axis?
It stands for the value of that coordinate.
What is the value, the x value of this coordinate?
1.57.
That's right. How did I get that 1.57?
Because we used pi divided by 2.
That's right. So my point is the hash mark stands for pi over 2.
Okay, okay.
So then what would this hash mark stand for if it's at an equal distance?
Pi over 3.
Well, careful. What it would be stand for pi over 2 plus pi over 2, right?
Okay.
Which would just be pi. Okay, so in any case, this gives us hash marks that are more useful for trig functions, usually. And then on the y-axis, they stand for different things. So what's the y hash mark stand for this point?
It stands for the y-coordinate at x over 2.
Pi over 2.
Right.
And what is that y-coordinate?
That y-coordinate's just 1.
Right. You already figured that out earlier, but the calculator also tells us that down here, right? So these hash marks still stand for 1, 2, 3, 4. So in any case, when you're working with trig functions, it helps to go to the zoom trig. Oftentimes, that's often the best zoom, although not always. Okay. All right, that's just a trick. Sometimes that's not the best zoom, but sometimes that's a helpful trick. Okay.
So, sorry. So with that line, would that represent the slope of the function that we're looking at?
Which line?
The graphical output on the calculator, because it's a little bit different than before, isn't it?
Let's
or is
see.
it the same?
I think it's this. Well, let's see. I'll go back to what I had before. So what you had? How do you go back to what you had before?
We would just go to zoom standard.
Standard, right? Standard is the default.
I guess it's the same.
It's the same. It's just zoomed in.
Okay.
So no, it doesn't represent the slope. We're still graphing the original function. Changing the zoom doesn't change the function. It just changes how zoomed in you are. Okay. It's a lot like you can zoom in and out, like you've been zooming in and out on your own drawing program.
Okay.
All right. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.